All right, guys, today we're going to look at Lab 27. Lab 27 is parallel capacitance, and you should recall that in parallel circuits, when we put capacitors in parallel, we are adding them together and therefore increasing the capacitance. We're basically increasing the plate size of the total capacitor here. So we're able to increase the capacitance, and we should be able to see that today in an RC circuit. Going back to Lab 25, we constructed an RC circuit, a resisted capacitive circuit, and in that lab, we changed the resistance, and we saw the effect on the change in the time constant, or the charge-discharge time in that circuit. There we were changing resistance. Here we're going to change capacitance. We're going to keep a fixed resistor and change the capacitance, and we should see a very similar result, a change in our time constant. Okay, to do this lab, set it up in Tinkercad. You're going to need an oscilloscope, a function generator, a 1K ohm resistor, and 3.1 microfarad capacitors. So here I have those items pulled out. I've already wired them up. Today I'm using a mini or small breadboard. One, to ease in our wiring as we move through the lab, and two, to also remind you, you should remember how to wire components up on a breadboard itself. So in constructing the circuit, we're going to look at our schematic down here at the bottom. We have our function generator set out here, and the settings for our function generator, we should have a square wave, 1 volt peak to peak, a DC offset that enables us to have a minimum voltage at 0, and a frequency of 200 hertz. So taking a look at my function generator settings here, here's my frequency, 200 hertz. I set my amplitude or peak voltage at 1. They're looking for a peak-to-peak voltage of 1. And so there's my amplitude setting. In order to achieve 0 volts on the baseline there, we need to set an offset of half of 1. Half of 1 is 0.5 volts. So set your DC offset at half of 1, and that way the line will be, your baseline will be at 0. Our square wave is the function that we're putting out here in our circuit. Now we also want to make sure our oscilloscope is set up to read a cycle for 200 hertz. So just a reminder here, let's take our calculator out. If the frequency is 200, take the inverse of that, 1 divided by 200, and that's going to give you a period of 0.005 seconds, or 5 milliseconds, when we're looking at one cycle in this waveform. So if there's 5 milliseconds for one cycle, you can, we'll go ahead and right now we'll set our time per division at 5 milliseconds. That should capture one full cycle in one of these squares on the oscilloscopes. Later on, we'll go back and we'll set that to 0.5 because we have 10 squares across here. We want to just look at one oscilloscope cycle, so we'll show you the difference there. But right now, let's set our oscilloscope up at 5 milliseconds per division based on the frequency math. The inverse of the frequency, 1 divided by 200, gave us a 0.005 seconds, so for a period of the waveform. Okay, let's look at the circuit setup now. So looking at the schematic, you have your source, positive side is resistor, we have a 0.1 microfarad capacitor, and we're back to the source, the function generator. So modeled over here, here's our function generator. It is set to the 200 hertz frequency with our 1 volt peak to peak amplitude. To get a 0 line base, we have an offset of half of 1, so 0.5 volts, and our square wave. Going through the positive line, we come into our 1K ohm resistor, and that 1K ohm resistor is tied into the positive bus line on this small proto board here. Off that bus line, we go through our first capacitor, our 0.1 microfarad capacitor, and then back to the negative bus line where we return to our function generator. The oscilloscope is set up to read across the capacitor. So we're reading across the capacitor by tying it into the bus line there. And that mirrors these two probes over here in our schematic. Now, looking at the time per division setting on my oscilloscope, I have that time per division setting set at 5 milliseconds. Where did that come from? That comes from our period calculation based on the frequency. So if you pull your calculator out, remember the inverse of the frequency is your period. You take 1 divided by 200 hertz, and that equals 0.005 seconds. 0.005 seconds is 5 milliseconds. That means that one period of the waveform is going to cover 5 milliseconds. If I have 5 milliseconds per division, that means I should have 10 cycles of the wave across my oscilloscope screen. We will change that so we can do a more precise reading, but for right now, let's look at that setting. Okay, so our goal here is to measure and record the times of charge and discharge looking at the slopes on the scope. So let's go ahead and start our simulation. And here you see, we'll zoom in on the scope itself. You see that we do have those 10 cycles I previously talked about. 10 full cycles, one cycle is covering the predicted one division, the 5 millisecond division, but this really isn't helping me record the charge and discharge time to really get a close look at it. So let's modify the settings here, and instead of 5 milliseconds to the division, take 1/10 of that. That would be 0.5, or another way of seeing that is 500 microseconds when we're looking across here. So now at 0.5, we do see just one cycle, and it's a little easier way of looking at the data that's on the screen there. So here's our charge, and then it levels off, and it's flat. Okay, the discharge starts here and picks up here. Unfortunately, with the Tinkercad oscilloscope, we can't adjust the trigger, but this does give us a very good feeling. If this is where the discharge is, and it continues here, it gives us a very good feeling that we're really talking about one square or one division. In other words, we're seeing the discharge of this wave to be a full 0.5 milliseconds. And the same thing with the charge here. We can pretty much see there's one division to charge. So it takes 0.5 milliseconds to charge. We'll divide your 0.5 by 5, and you know that the time constant in this case is 0.1 milliseconds for a charge and charge. Now, based off what we've seen in our previous labs, we know that in parallel we should see an additive effect when we add another capacitor in parallel. So let's stop our simulation and go ahead and add a wire in here. This is our second capacitor adding in parallel. We're essentially doubling the capacitance now. So instead of 0.1 microfarad, we have 0.2 microfarad. And what we should also see is an extension by double the amount of time. So instead of 0.5 milliseconds, we should see a full charge cycle of 1 full millisecond here as we're doing our calculations. So let's see what that looks like. And here is a very similar waveform, but yes, there is a change. And again, you're going to have to look at, we can kind of come down here and see as we come down in the discharge and pick it up here, that we are about, well, we're probably a little into a half on this side, a little half here. So that is more or less 2 squares or 2 divisions, and 2 times 0.5 is 1. So you see 1 millisecond coming across here in discharge. Our charge time going up, and we don't really stop until we're right about here. So again, that represents 2 divisions, and if each division is worth 0.5 milliseconds, it takes 1 millisecond to fully charge. Let's see what happens when we add our third capacitor. So let's add our third capacitor in here, and we're going to start our simulation again. And here again, looking at a pretty similar waveform, but notice it's flattening out here in a longer scale. So looking, and again, easier to start by looking at the discharge. We discharge about halfway into this square here. You come down and you pick up here, and there's your there's a second and third square piece here. So what we're seeing is about a square and a half in terms of the discharge of this waveform, and that makes sense. We're increasing it. We're now at 0.3 microfarads in our capacitance, and so we're essentially adding another 0.5 milliseconds to the charge and discharge. We should be able to prove that with some calculations. So looking at the review here, the first section, we've tested those characteristics of the parallel capacitor, and we did that incrementally. We were able to see that pulsating DC signal, the square wave that we put on it, was able to illustrate the charge-discharge slopes, and essentially seeing that we effectively doubled the capacitor value with the second one, and then added another half into that when we put the third one on. And this was the scale there. The time constant calculation that goes in here is still and always the same, where T is equal to the product of resistance and capacitance. If you pull the calculator back out, we can take a look and prove what we measured out here on the screen. Okay, let's see how that equates with the calculator out here on the screen. So remember, we have 0.1 microfarad per capacitor, and we have 3 capacitors. So if we take 0.1 microfarad times 3, or really it's an additive situation, it equals 0.3 microfarad. That is our total capacitance here in parallel, because it does add up. This plus this plus this is our total capacitance. 0.3 microfarad is our total capacitance. Our resistor is 1 k ohm, so take our 0.3 times that resistance of 1 k ohm, and it gives us a value of 0.3 milliseconds. Because we're dividing k ohm, we're multiplying k ohm and microfarad, our answer is in milliseconds. If we were doing ohm and farad, our answer would be in seconds. So here, our time constant is 0.3 milliseconds. Now remember, a time constant is 1/5 of the total amount of time it takes to charge and discharge. So let's multiply this by 5, and you see it should take a full 1.5 milliseconds to charge and discharge. And we can prove that over here on the graph. Let's look at the discharge time here. You see here's 1 full division, 2 full divisions, and if each division is 0.5 milliseconds, right there is 1 millisecond, and yet we have a half over here. Here's half of a division, so there's our 1.5 milliseconds that we see for the 3 parallel capacitors. You can do the same thing for 2 and the same thing for 1. You take your 0.2 times your 1 k ohm, and that time constant is 0.2 milliseconds. You have 5 of them times 5, and that equals 1 full millisecond to charge and discharge, and we saw that when we put that on the oscilloscope. You can do the same thing with your single. 0.1 times 1 k ohm equals 0.1 milliseconds as your time constant. You have 5 of them, so times 5, that gives you your 0.5 millisecond full charge and discharge when you had your single capacitor. So that is the experiment, and the calculations worked out. One final thing, I'll make a note to the bottom of look at the bottom of the lab sheet, and I want to clarify a statement there. On the bottom of the lab sheet, right here, they mention that we would have a discrepancy in our calculations due to the internal resistance experienced within the function generator. Tinkercad as a virtual function generator does not have the internal 600 ohm resistance. If we were to do this in the lab, our function generator does. In fact, it's a 500 ohm internal resistance on our function generators at school. So to account for that, we would have to add that to our 1 k ohm for a total of 1.5, or in this case, 1.6 k ohm when we did our math. And that would make up for any discrepancies that we might see in the oscilloscope. For our virtual experience, we don't have any discrepancies, so we don't have to worry about that. And so the very last question here doesn't need to be accounted for. Go through and fill this out. I understand that you won't have this chart in your Google Doc, You can make your own table that's very similar to this as you put your measured data